In this chapter, we proceed to the second part of chapter 1, which is about introduction to proof. So proof is very important in mathematics. Why? Because proof is a valid argument that establishes the truth of a mathematical statement. All right, so that means the truthness of a mathematical statement can be established by using a proof. So in order to provide the proof, we can use hypothesis of the theorem, but if any, we also can use axioms, which is assumed to be true, and also we can use previously proven theorems. Okay, so now we learn about some important terminologies in proof. Okay, so we have a hypothesis. What is hypothesis? So basically, hypothesis is an idea or theory that is not proven yet. Okay, not proven, but that leads to further study or further investigation. So that is what we call as hypothesis. Then we have axiom. So what is axiom? So basically, axiom is a statement that we assume to be true. It is a statement, then we assume that that statement is true statement. Okay, so that is what we call as axioms. Okay, next is the proof. What is proof? So proof is a valid argument that establishes the truth of a theorem. Then theorem. So theorem is a statement that can be shown to be true. Okay, so once the statement can be shown to be true, then it is a very important statement. So we call that kind of statement as a theorem. Okay, so I mentioned just now about the importance of that statement because different level of importance, so we call that statement as different with a different name. Okay, so for the most important statement that proven to be true, then we call that kind of statement as theorem. We also have another kind of statement that is proven to be true, but it is less important than theorem, so we call it as propositions. So proposition is less important than theorem. All right, then another one, we also have lemma. Okay, so lemma also is a less important theorem, but in addition, it is helpful in proof for other results. So we can use lemma to prove another theorem, for example. Okay, so that's the difference between propositions and lemma. So for proposition and lemma, both statements are proven to be true, but then they are less important than theorem. But then the difference between propositions and lemma is helpful to prove another result. For example, we use lemma to prove theorem. Okay, so instead of providing lengthy proof for one theorem, so we can separate that proof into several lemma. Okay, then we combine together, come out with a single proof for that theorem. Okay, so now another one is we have also corollary. So corollary basically is a theorem, and this theorem can be established directly from a theorem that has been proved. That means from existing theorem, we can establish another theorem. So that theorem is what we call as corollary. Then we have conjecture. Okay, so conjecture again is a statement that is being proposed to be true. Okay, it is proposed to be true, usually based on some partial evidence. Okay, based on some partial evidence, a heuristic argument, or the intuition of an expert. When a proof of conjecture, when a proof of a conjecture is found, automatically that conjecture will become a theorem. Okay. So for any statement that is not proven yet as a true statement, we call it as a hypothesis. Then if we have a partial evidence about the truth not of the statement, so we can call it conjecture. But once the conjecture is proven to be true, then it can become a theorem. Okay, so we start from the hypothesis. So hypothesis, there is no evidence that the statement is true. They're followed by conjecture, where we have a partial evidence about the truth not of the statement. Once we prove that conjecture, so it becomes theorem. See, theorem is a proven mathematical statement, so it is the most important statement of fact in mathematics. So it also more general compared to the corollary, lemma, and proposition. So for corollary, it is a theorem and it is established from the existing theorem. So we call it as corollary. Then we have a less important theorem, what we call as lemma. So lemma is helpful to prove other results and also can be used to prove a theorem. Then finally we have proposition, which is another statement that is proven to be true, but it is less important than theorem, and it is not used to prove any other result. So we call it as proposition. Okay, now we move to the next topic regarding definition, because other than proof, we also have definition, which is very important in mathematics. So new mathematical objects are created by new definitions. Okay, new mathematical objects are created by new definitions. For example, the idea of imaginary and complex numbers. So the idea started from the definition of I, where I is defined as a number such that I square equal to -1. Start from this simple definition. So mathematicians come up with variety and various idea about the imaginary and complex numbers. Okay, start from the simple definition. So it results a very important topic about complex numbers. Okay, so the properties of those objects also can be created by using definitions. Then in definition also helps to describe the relationship between several objects. A new definition could be start with a lengthy investigation of new mathematical questions and discovery. Then lemma, theorem, or proposition could be derived from definition. We start from definition, and from that we can start from maybe proposition, followed by lemma, and finally we come out with the most important result, which is known as theorem. So consider the following occurrence. Okay, let's say we have several cases when we divide any integer by 2. So the outcomes can be either integer or non-integer output. Okay, we have any integer. Okay, when we divide by 2, so the outcome can be integer and can be non-integer. So from that occurrence, so we can come out with a conjecture that any integer can only yield either integer or non-integer as output when it is divided by 2. Okay, so this statement can be called as conjecture because it is partially we have partial evidence of this. Okay, we can do some examples, and then we can obtain some results from our example, but then there is no proper proof or proper evidence of this statement, so we call it as conjecture. So from that, okay, so we can divide basically integer or any integer basically can be divided, okay, by into two groups. Okay, and the first one we call as even number, and another one is what we call as even number. So for even number, it can be divided by 2. That means without any remainder. But on the contrary, for the odd number, when we divide by 2, so there is a remainder. Okay, so that is the idea about the even and odd numbers. Then we want to come out with a proper definition for the even and odd numbers. Okay, so the even and odd numbers can be mathematically defined as follows. So first of all, we define one variable, one parameter. Let's say we have a, which is an integer. A belongs to the set of integer. Then the integer a is an even number if a over 2 equal to k, where k is an integer. Alright, so a over 2 equal to k, where k is an integer. For example, okay, let's say a equal to 4. So 4, when we divide 4 by 2, so the outcome is 2, where 2 also is an integer. What else? We have a 14. Okay, so 14 divided by 2, the outcome is 7. Again, 7 is an integer. Okay, so any integer a, when we substitute to this fraction, so if the outcome is an integer, then a is called as even number. So how about odd number? So the integer a is an odd number if the fraction of a over 2 it is equal to k plus 1. Okay, when we divide a over 2, so the outcome is equal to k plus 1, where k is an integer. For example, 7. When we divide 7 by 2, so the outcome is 3 plus 1. Okay, so 3 is an integer plus 1. So any integer that can be formed like this, it is referred to as odd number. So this is the proper definition of even number. So we define what kind of number is the a. Okay, so a is an integer. Then what is the condition to be a even and odd number? So we provide the condition. So any number or any value that satisfy the given condition, so follow the definition for the even and odd numbers. Okay, so from that definition we can derive lemma. Okay, as I mentioned before, from one definition we can derive a proposition, we can also derive lemma, and finally the biggest result we can also derive a theorem. Okay, let's see how to derive a lemma from the previous definition. So we consider lemma number 1. Let a and b be integers. Okay, if a is an even number and b is an odd number, then a minus b is an odd number. Okay, this is a statement. So in order to be a lemma, it must be proven as a true statement. So we need to provide the proof in order to establish the truthness of the statement in this lemma. Okay, we start from the given information. We have two integers, a and b. So, okay, so the first step is to assume that, the given condition, because this is if and then statement. Okay, conditional statement. So we have if a is an even number and b is an odd number. So we start from our assumption that the given a is an even number and the given b is an odd number. So we are referring to the previous definition. Because a is an even number, so it can be formulated as a equal to 2k. Alright, so b is an odd number, so it can be formulated as b equal to 2l plus 1, where k and l can be any integer. Okay, so from that, we have a minus b. Okay, we want to prove that if a is an even number and if b is an odd number, so a minus b is an odd number. So we have a minus b, it is equal to a equal to 2k minus b equal to 2l plus 1. Okay, we substitute the value for the a and also the value for the b. Then we expand this equation. Okay, we eliminate the parentheses. Okay, so after we expand this one, so actually we have 2k minus 2l minus 1. Okay, but then in order to show that a minus b is an odd number, okay, our aim is to show that a minus b can be represented by 2k plus 1, where k can be any integer. Okay, so we need plus 1 at the end of this equation. So how to come up with plus 1? So we know that negative 1 actually is equal to negative 2 plus 1. Okay, it is same value. So we can replace negative 1 by 2k minus 2l minus 2 plus 1. So this equation remains true because negative 2 plus 1 equal to negative 1. Alright, so we enclose this value, okay, 2k minus l minus 1 plus 1. Okay, so next we know that, okay, because k and l are integer, okay, so k minus l minus 1 again is an integer. Okay, so k minus l minus 1 again is an integer. We can say that integer as m. Okay, we can replace that integer as m, where m is an integer. Alright, thus, so a minus b finally can be represented as equal to m plus 1. Because m is an integer, so based on the previous definition, so we can say that a minus b is an odd number. Okay, so at the end of a proof, we need to provide this solid square, okay, to indicate this is the end of our proof. Okay, now we move to the lemma number 2. We also can derive the following lemma from the previous definition. So let's see, we have integer c. So if c is an odd number, then c plus 1 is an even number. So that is the statement. So in order to be a lemma, we need to prove this statement. Okay, so we start from the given information. We have c. So we assume that the given c is an odd number. Okay, that's our assumption. Okay, so we assume the given the given condition is true, and our aim is to show that if c is an odd number, so we can show finally that c plus 1 is an even number. So we start from our assumption. So we assume that let c equal to 2k plus 1 because we assume c is an odd number. Okay, where k can be any integer based on the definition for the even and odd number. Thus, so c plus 1, because we need to prove c plus 1, so we have a c plus 1 here. So c plus 1 equal to 2k plus 1 plus 1. Okay, because this is come from c plus 1. Okay, then we combine these two numbers based on addition operation. So we have 2k plus 2. Okay, so k plus 2, we can factorize this one, becomes this equation. So we have 2k plus 1. Okay, so because k is an integer, so integer plus 1, the outcome is an integer. Okay, we let the integer as L. Okay, L can be any integer. The c plus 1 can be rewritten as 2L. Okay, so based on the definition for the even and odd number, so any number that can be represented by 2L, where L is an integer, is considered as even number. So we have shown that c plus 1 is an even number. So that is the end of this theorem. The end of this the proof of the lemma. Okay, now the previous two are considered as lemma, and this is considered as theorem. Okay, it is more general than it looks more important. So in this theorem, it says that there is no integer that is even that is both even and odd number at the same time. Okay, there is no integer that can be even and odd at the same time. So that is the theorem. So our task is to prove this theorem. So let's say we have one integer a. Okay, suppose that a is both even and odd number. Okay, our assumption is a satisfies the condition that it is an even and at the same time it is also odd number. Thus, a can be represented as a equal to 2k and also a equal to 2l plus 1, because a is an even number, so it can be represented like this. Because a also is an odd number, so it can be represented like this based on the definition for the even and odd numbers. Okay, don't forget to provide that, because you introduce new variable k and l, so make sure you mention what kind of numbers are these two variables. So these two variables are integer. Okay, thus, so because we have a equal to a, okay, so we can replace a equal to 2k and a equal to 2l plus 1. Okay, so we rearrange this equation. We take 2l to the other side, so we have 1 equal to 2k minus 2l. We factorize, so we have 1 equal to 2k minus l. Since k and l are integers, so the subtraction of integers, the outcome is an integer. Suppose the integer is m. Okay, m is an integer. Again, because we introduce new variable, so you have to mention that what kind of number is that. So it is an integer. Thus, from that, we have 1 equal to 2m. Okay, 1 equal to 2m. So we can take 2 to the other side, so we have half equal to m. But then based on our definition, m is an integer. So how come half equal to an integer. So this is what we call as a contradiction because it is false. Okay, half is a non-integer. Okay, half is a rational number. It is not an integer. Okay, half. So this is what we call as contradiction. So because of that, our conclusion is therefore a cannot be both even and odd number at the same time. Okay, so this is the way how we prove through the contradiction method. So later I provide details about the contradiction method of proof. Okay, this is the end of this proof. Okay. So consider the following occurrences. Any integer bigger than 1 can be factored to at least 2 factors. Okay, at least 2 factors, 1 and itself. At least means it can be greater than or equal to. So any integer bigger than 1 can be factored to exactly 2 factors only, which are 1 and itself, so is known as prime number. Okay, so any integer bigger than 1 that can be factored to more than, okay, previously exactly 2. There are only 2. The first one is the integer 1 and another one is the itself. Okay, only 2 integers that can divide that number. So we call that number as prime number. So for any integer number greater than 1 that can be factored to more than, okay, more than 2 factors. Sorry, it is not equal to, it is greater than because more. Okay, more than 2 factors. Okay, that means we have another factor other than 1 and itself. So that kind of number is called as composite number. Okay, so from these two statements we can formally or properly define the prime number as given in this definition. So how to define a prime number? Okay, let P be a positive integer. Okay, we want to introduce one variable, so we need to make sure to specify what kind of number is that. So in this particular case, P is a positive integer. And the second condition is P must be greater than 1. Okay, so that means the smallest number for P, okay, the smallest possible value for the P is 2. So it can be 2, 3, and so on. Because 2, 3, and so on satisfy both conditions. They are positive integers and they are greater than 1. Okay, then the integer P is a prime number if it is divisible. Okay, divisible means when we divide, then there is no remainder. Or in other words, when we divide, then the outcome is an integer. So this kind of number, okay, is called, the integer P is called a prime if it is divisible only by 1 and itself. Okay, that means when we divide P by 1, the outcome is an integer. And when we divide P by itself, the outcome also is an integer. But if we divide P by other numbers other than 1 and itself, so the outcomes are non-integers. So that is the definition for the prime number. So otherwise, other than prime, so we have one kind of number, what we call as composite number. So that is the way how to derive the definition. Okay, now we move to the methods of proving theorems. So how to prove a theorems? We have several methods. To construct proof, we need all available ammunition, including a powerful battery of different proof methods. So we have several types of proof methods. These methods provide the overall approach and strategy of proof. Understanding of these methods is a key component of learning how to read and how to construct mathematical proof. Once we have chosen the proof method, then we can use axiom, we can use definition of terms, we can also use previously proved results and rules of inference to complete the proof. Okay? So the first method is what we call as direct proof. A direct proof of a conditional statement. Okay? Like in the previous definitions, we have if and then definition, kind of definition. Okay? For example, for the even number, if a equal to 2k, then it is known as an even number. So we have if and then kind of statement. Okay, so this is the conditional statement. If P then Q. A direct proof of a conditional statement if P then Q is constructed when the first step is the assumption that P is true. Okay, we assume that the given condition is true. Subsequent steps are constructed using rules of inference, with the final step showing that the Q, okay, Q also, the statement Q also must be true. Alright, so if we assume P is true, then Q also must be true. So that is the way how we do the direct proof. A direct proof shows that a conditional statement if P then Q is true by showing that if P is true then Q also must also be true. So the combination P true and Q false never occurs. Okay, if you still remember about the truth table for the conditional statement, if P is true, if Q is false, so the outcome is false. Okay, so the combination of P true and F false never occurs. Okay, now we consider the following example. Give a direct proof of the theorem. If n is an odd integer, then n squared is odd. Okay, this is the given statement. So we need to prove this statement by using direct proof, because the question specify the way how to prove the given statement. Okay, you cannot use other method because the question specify you need to use the direct proof. Okay, let's see how to prove this statement. Note that this theorem states that for all n, Pn, okay, for all n, if Pn then Qn, where Pn is n is an odd integer and Qn is n square is odd. Okay, we have two statements. Okay, we have two statements with the same input n and n. For the statement Pn, it is n is an odd integer. For statement Qn, n square is odd. So if we combine together in this conditional statement, it becomes if n is an odd integer, then n square is odd. Okay, just like the given original statement. So now, in order to prove this statement using the direct proof, first of all, we need to assume that the hypothesis of the conditional statement is true. Okay, the hypothesis of the conditional statement is true. So where is the hypothesis? The hypothesis is the Pn statement. So we need to assume that n is an odd number. Okay, or n is an odd integer. By the definition of an odd integer, so we have n. So because n is assumed to be odd number, so it can be written as 2k plus 1. N equal to 2k plus 1. Okay, where k can be any integer. Then, okay, our interest now is to know about the square of n. So we have n square here. So n square equal to, because n equal to 2k plus 1, we substitute to here. So it becomes 2k plus 1 square. So we expand, we come up with this equation. We have 4k square plus 4k plus 1. And then we can factorize. So we have 2 in parentheses 2k square plus 2k plus 1. Okay, so inside the parentheses, again, because k is an integer, so 2k square plus 2k, you can replace k with any integer. The outcome always is an integer. Okay, you can substitute k with any integer. For example, what? K equal to 0. The outcome is 0. 0 is an integer. What else? You substitute k equal to 1. So the outcome is equal to 3. Okay, so 3 is an integer. So if you can substitute k with any integer, the outcome is always integer. So we can substitute this value with another variable. Let's say it is equal to L. So we need to define L is an integer. So now n square can be rewritten as 2L plus 1. So by definition of an odd number, so we can conclude that n square is an odd integer. Okay, because based on the definition, 2L plus 1 is an odd integer. So that is the end of this proof. Okay, so I think the direct proof is quite easy. So for if and then a statement or conditional statement, so we need to assume the given hypothesis is true. So our task is to show that the another statement after the condition is also true. Okay, so now we move to the proof of contraposition. So make use of the fact that the conditional statement if P then Q is equivalent to is contrapositive, if not Q then not P. Okay, so these two statements are equivalent. If P then Q, so it is equivalent with if not Q, then not P. So what does it mean? That means the conditional statement if P then Q can be proved by showing its contrapositive is true. Okay, in the previous method for the direct proof, we directly show this statement is true. That is why we call it as direct proof. So for the contraposition method, instead of proving this one, we prove this one as true. Okay, we prove that the not Q, if not Q is true, then the not P also true. If not Q, then not P. If this statement is true, automatically this one also true because they are equivalent. Okay, so in contrapositive, we need to show that this statement is also true. If not Q, then not P. Okay, example. Proof by contraposition. Again, the question specify the way how to prove this statement. So proof by contraposition that if n is an integer, then 3n plus 2 is odd. Okay. If n is an integer and 3n plus 2 is odd, then n is odd. That is the given statement. Okay. So now we need to prove this statement by contraposition method. Alright, the first step is to assume that the conclusion. Okay, because in contraposition, we need to prove that not if not Q, then not P. Okay, so we need to assume that the conclusion of the conditional statement, if n is an integer and 3n plus 2 is odd, then n is odd. The conclusion of this conditional statement need to be assumed as false. Okay, so we need to assume that the conclusion of the given original statement, okay, the given original statement, we need to assume that the conclusion is false. Okay, so in other words, based on the given condition, in other words, we need to assume that 3n plus 2 is odd, then n is even. Okay, because in the original statement, if 3n plus 2 is odd, then the conclusion n is odd. So we need to change the conclusion. Our assumption is if 3n plus 2 is odd, the n is even. Okay, this one even, the original one is odd. So we need to assume that the conclusion of the original statement is false. If the conclusion in the original statement n is odd, so in this assumption, we need to assume that the conclusion is false. So n is even. Since n is even, okay, then by definition, it can be written like this. N equal to 2k, where k can be an integer. Okay, then we have 3n plus 2, the original statement. 2n plus 2 equal to, we substitute n by 2k plus 2. And then we expand this one, we have 6k plus 2. Okay, again, we can factorize, it becomes 2, 3k plus 1. So since k is an integer, so 3k plus 1, if you replace k with any integer, the outcome also is an integer. So we can substitute 3k plus 1 as L, where L can be any integer. Thus, 3n plus 2 can be rewritten as equal to 2L. 3n plus 2 equal to 2L. So this tells us that 3n plus 2 is even, because 2L by definition, where L is an integer, so 3n plus 2 by definition is even. Okay, 3n plus 2 is even, but then in our assumption, 3n plus 2 is odd when n is even. Okay, so what does it mean? This is what we call as the negation. Okay, this is the negation of the premise of the theorem, because the negation of the conclusion of the conditional statement implies that the hypothesis is false. Okay, the negation of the conclusion of the original conditional statement, because in our assumption we let the conclusion of the original statement as false, so the outcome is we come out with the negation. Okay, so that means the original statement is true. So that is what we call as the proof by using contraposition. Okay, we have another example here. Prove that if n equal to ab, where a and b are positive integers, then a is less than or equal to square n, or b is less than or equal to square n. Okay. Okay, again. If n equal to ab, where a and b are positive integers, then a is less than or equal to square root of n, or b is less than or equal to square root of n. So let's see how to prove this theorem, this statement. Okay, so the question doesn't specify, so you can use actually direct proof, but then because we want to, it is in the section of a contraposition method, so we want to prove this statement by using contraposition. Okay, let's see how to do it. So in the original conditional statement, okay, if P then Q. Alright, so in contraposition we want to prove that if not Q then not P. Okay, so we need to assume that the conclusion is false. The conclusion of the original statement is false. Alright, so assume that the conclusion of the conditional statement, the original conditional statement, okay, a less than or equal to n, or b less than or equal to square root of n, we need to assume that this one as false. Okay, so when false, what does it mean? If true is a less than or equal to square root of n, so the false, the negation of this one, it is, okay, we need to assume that it's false. So how to make it false? Using the meaning of disjunction together with De Morgan's law, so we see that this implies that both a less than or equal to square root of n and b less than or equal to square root of n is false. This implies that a is larger than square root of n and b is larger than square root of n. Previously, they are assumed to be less than or equal to, so the opposite of this one is greater than. Okay, so the false statement for the given for the original conclusion, now it becomes a greater than square root of n and b is greater than square root of n. We can multiply these inequalities together, okay, using the fact that if s is greater than 0 and less than t, and u is greater than 0 and less than v, then s times u is less than t times v. This is fact. Okay, you can replace s, t, u, and v with any number, so this is always true. Okay, so we want to use this fact to obtain a times b greater than square root of n. Greater than square root of n multiply square root of n. Okay, that means a multiply b square root n multiply square root n. So because square root n times square root n, so the outcome is single n. Okay, so this shows that means we have a, b, now it becomes greater than n. After we multiply square root n and with square root n, it becomes single n. Okay, now we're referring back to the original statement. In original statement, we are given that n equal to ab, but then we obtain ab greater than n. So what does it mean? That means it is a contradiction. Okay, ab not equal to n. because AB greater than N, that means A and B not equal to N. In our assumption, we have AB equal to N. So this is what we call as contradiction, which contradicts the statement N equal to AB, because the negation of the conclusion of the conditional statement, I mean the original conditional statement, implies that the hypothesis is false. So that means the original condition statement is true. So this is the way how to prove by using contraposition method. The key point here is we need to, the first step is to assume that the conclusion of the original conditional statement is false. Okay, so from that we prove until we meet a contradiction. Okay, once we found a contradiction, then we come up with the conclusion that the original statement is true. Okay, now we have another example. Prove that if n is an integer and n square is odd, then n is odd. Okay, so this is our P, this is our Q, the original one. Okay, so our assumption, because we want to use the contraposition method, we need to assume that we have not Q. Okay, that means the original Q, we negate the original Q, it becomes false. If not Q, then not P. So we need to assume that the original Q is false. If the original Q n is odd, so now it becomes even. Assume that n is even, which implies that n equal to 2k. Okay, because it is an even number, so it can be written as 2k, where k can be integer. So we need to show that this hypothesis implies the conclusion that n square is even. Okay, n square is even because we want the conclusion is not P, so not P, because P is odd, so not P is even. Okay, n square is even. Thus, n equal to 2k, so we have n equal to 2k, so for the square of n, so n square, we have 2k square equal to 4k, so 4k can be rewritten as 2 times 2k square. Okay, because k is an integer, so 2k square again is an integer. We can replace it by L, where L can be any integer, so n square can be rewritten as 2L. Okay, so this implies that n square is also even. So we have proved that if n is an integer, then n square is odd, then n is odd. Okay, because we have shown that this contraposition statement also true. Okay, now finish with the contraposition method, we move to the proof by contradiction method. So suppose that a statement P is true. Furthermore, suppose that we can find a contradiction Q such that not P. If not P, then Q is true. So contradiction of Q means we need to make the Q as false. Okay, we need to find a contradiction of Q, because the Q is false but not P, then Q is true. Okay, this one is false, this one is true. So we can conclude that not P is false. Because not P is false, that means P is true. Okay, because not P is false, not P is false, then P is true. Okay, but the question now is, how can we find a contradiction Q that might help us to prove that P is true in this way? Okay, so because the statement R and not R is a contradiction, okay, whenever R is a proposition, so we can prove that P is true if we can show that not P, if not P, then if not P, then R and not R is true for some proposition R. So this kind of proof is what we call as contradiction method. So let's see some examples to make it clear. Okay, the first example, show that at least, okay, at least that means greater than or equal to. at least 4 of any 22 days must fall on the same day of the week. That is the statement. So our task is to prove this statement by using contradiction method. Okay, let's see how to do it. So first of all, let P be the preposition at least 4 of any 22 days. Okay, chosen days fall on the same day of the week. Okay, so our original P is the given statement. At least 4 of any, okay, 4 of any 22 chosen days fall on the same day of the week. That is our statement P. So our assumption is we need to assume that the not P is true. Not P is true. So if this is P, so what is not P? Okay, so not P means at most. Okay, because that is at least, greater than or equal to. So the contradiction of greater than or equal to, the opposite is at most. That means less than. Okay, so at most 3 of the 22 days fall on the same day, same day of the week. This one off. Okay, so almost the same statement, but then we make it in contradiction way. Previously at least 4, now it becomes at most 3. Okay, because there are 7 days of a week. Okay, we have Monday until Sunday, so we have 7 days in a week. This implies that at most 21 days could fall on the day. Okay, so in a week we have 7 days, so 7 times 3 weeks, so we have how many days? 21 days. Okay, because there are 7 days of a week, this implies that at most, okay, based on our previous assumption, at most 21 days could fall on the day. But then this is a contradiction, because in our earlier assumption, okay, in the given statement, we have 22 days of consideration. We consider 22 days instead of 21 days. Okay, so that is what we call as contradiction. So this contradicts the premise that we have 22 days under consideration. That is, if R is the statement that 22 days are chosen, then we have shown that if not P, then R, and not R. So consequently, we know that the original statement P is true. So from this proof, we have proved that at least 4, okay, at least 4 of 22 chosen days fall on the same day of the week. All right, so now we have another example. Prove that the statement square root of 2 is irrational by giving a proof by contradiction. Again, you can choose another other method proof. Okay, other method to prove this statement other than contradiction in order to answer this question. So okay, so let's see how to prove this statement by contradiction. So let P be the proposition, P the original proposition, P is irrational. So to start a proof by contradiction, we need to assume that not P is true. Okay, so if P is in the original statement, P square root 2 is irrational, so not P is square root 2 is rational. Okay, so the negation of P is not 2 is rational. So we need to assume that the square root of 2 is rational and this statement is true. Okay, that is our assumption. So from that, we will show that assuming that not P is true leads to a contradiction. That means from this assumption, at the end of our proof, we can come out with a contradiction. Okay. Alright, so back to our assumption. So because we assume that the square root of 2 is rational, that means there exist two integers a and b, okay, where the square root of 2, because it is rational, so it can be written in a fraction form. A and b are integers, and another condition is b must not equal to 0, otherwise it becomes undefined. Okay. And A and B have no common factors. That means this is the simplest fraction lah for A and B. There is no other common factor for A and B. Okay. Because the square root of 2 equal to 1 over b, then both sides of this equation are squared. So it follows that, okay, if we put square, this one square, this one also square. So we come out with this equation. We can eliminate the third. It becomes 2 equal to a square over b square. Hence, we can rearrange this one. We can take b to the other side. So it becomes 2b square minus a square. So by definition of an even integer, okay, it follows that a square is even. Why? Because it can be written as 2b square. Because b is an integer, so b square also is an integer. Alright, so because a square can be written as 2b square, where b square is an integer, so basically a square is an even number. Okay, next, we use the fact that the a square is even, okay, because a square is even, so a also must be even. Okay, this is fact, so we can use this fact. If a square is even, then a also must be even. So furthermore, because a is even, by the definition of even integer, so a can be written like this. A equal to 2c, where c can be any integer. Okay, so we replace a equal to 2c to this equation, so it becomes this equation. 2b square equal to 2c square, it becomes 4c square. Okay, dividing both sides of this equation by 2 give us this new equation. So because c is an integer, so c square also is an integer. So that means b square is written as b square equal to 2c square, where c square is an integer. So by definition, b square also is an even number. Again, we can use the fact that if a square of an integer is even, then the integer itself must be even. So we conclude that b also must be even number as well. Previously we have shown that a is an even, and this time we have shown that b also is an even. We have now shown that the assumption of not p leads to the equation square root of 2 equal to a over b, where a and b have no common factors. Okay, where previously we assumed that a over b is the simplest form, where a and b don't have any other factor. So but now we have shown that from this assumption, we obtain that a is an even number, b also is an even number. So when both numbers are even numbers, that means both numbers have a common factor, which is 2. Okay, because these numbers can be divided by 2. Okay, so note that the statement that square root of 2 equal to a over b, where a and b have no common factors, means that 2 does not divide both a and b. Okay, so because our assumption that not p leads to the contradiction that 2 divides both a and b and 2 does not divide both a and b, then not p must be false. Okay, not p must be false. So that is the statement p square root of 2 is irrational is true. Okay, because not p is false, then p must be true. Okay, so our statement, our original statement, p is true. So from that, we have proved that the square root of 2 is irrational. Okay, we consider another example. Give a proof by contradiction of the following theorem. If 3n plus 2 is odd, then n is odd. Okay, so let's see how to prove this theorem. Let p be 3n plus 2 is odd. Okay, the statement p is 3n plus 2 is odd, and the statement q is n is odd. Okay, because we have conditional statement here. Okay, if p then q. If 3n plus 2 is odd, then n is odd. So our p is 3n plus 2 is odd, our q is n is odd. To construct a proof by contradiction, first of all, we need to assume that both P and not P are true. Okay, but then P and not Q. P and not Q are true. Okay, so that is, we assume that 3n plus 2 is odd and that n is not odd. So not odd, that means even. Okay, we assume this one is P, so that this one is not Q. We assume both are true. So for P, 3n plus 2 is odd, and for not Q, it is n is not odd, which is n is even. Because n is even, then n can be written as n equal to 2k, where k can be any integer. So this implies that 3n plus 2, we can substitute n equal to 2k, so it becomes 6k plus 2. Okay, again we can factorize, so it becomes like this, because k is an integer, so 3k plus 1 also is an integer, so we can replace as L, where L is an integer, so 3n plus 2, it is equal now to L. Okay, it is equal to 2L. 3n plus 2 equal to 2L, which implies that 3n plus 2 is an even number. Okay, is an even number. Alright, previously we assumed that it is an odd, but then we obtain it is an even. Note that the statement 3n plus 2 is even is equivalent to the statement not P. Because our P is 3n plus 2 is odd, but then we obtain 3n plus 2 is even. So it is equivalent to the statement not P. Because an integer is even if and only if it is not odd. Because both P and not P are true, then we have a contradiction. Because P and not P cannot be true at the same time. But then we obtain here P and not P are both true. So this completes the proof by contradiction, proving that if 3n plus 2 is odd, then n is. Okay, so this is your exercise. So that's the end of this lecture.